Okay, it's time to say goodbye to algebra and enter the wonderful world of circles. It's chapter 11. Let's go! So the first thing we need to be able to do is to name the parts of the circle fairly accurately. If you have a look here, we've got like some lengths on the left hand side and some areas on the right hand side, and we need to come up with the right names for them. So the first one we need to know, obviously our purple line here, is the diameter. And the diameter is basically any line that goes all the way across the circle through the center. So we could define it as that, a line across the circle through the center. The other one that you'll probably already know is in green here is the radius. And you might well know it as just half the diameter, and that would be fine. We can also define it as a line from the outside of the circle to the center of the circle. When we say center, we're talking about this central point here. Then we've got some slightly more obscure lines. So the orange one on the left, that's called a chord. And a chord is just a name for any line that goes across the circle. Technically, the diameter is a chord as well. The radius is not, because it doesn't go all the way across. In blue, we've got what we'd call a tangent. And a tangent is a line that just touches the circle. Or more generally, it's a line that just touches any curve. And the last one, in red here, this is called an arc. And that's just a part of the circumference. Not defined the word circumference here, I've assumed it's something we know, but circumference is all the way around the outside of the circle. It's like the perimeter. So if you wanted to write that down as well, circumference is equal to perimeter. And lastly, we've got these two little areas on the right hand side. So in green, we have like the classical pizza slice of the circle, and that's called a sector. Now there are some very specific ways to define it, but I think if we just think a slice from the center of the circle, I think that covers all of your is this a sector or not questions. And we've also got in red something called the segment. And a segment is one side of a chord. Technically we could pick either side and call them segments. The one that we've shaded in there, that's called the minor segment. The other side would be called the major segment. In circles, minor generally means less than half and major means more than half. So let's actually do something with these parts of the circle. So there are two formulas here that you should be more or less familiar with. That for any circle with a radius r and a diameter d, the area is pi r squared and the circumference is either 2 pi r or pi d. And all we're going to run through is a series of examples where we use this to do something interesting. If you want a bit more practice on just using circles, I would suggest you go back to chapter 7 and have a look through there. So let's look at our first question. We've got a square with an area of 64. We want to find the area of the circle. So to find the area of the circle, we're going to need to do pi r squared. To do that, we're going to need to know what the radius of the circle is. Now to do that, we're going to need to know what the length of the square is, and we can half it. So if the square has an area of 64, then it's got a length of the square root of 64, or 8, because 8 times 8 will obviously give me that 64. That means the radius is 4, and so the area of this circle is pi times 4 squared. Once it's to 2 decimal places, so 50.27. Don't forget your units, centimeters squared. For the second one, we've got to find the area of a quarter circle, given your answers in terms of pi this time. So area of a quarter circle is just going to be a quarter of pi r squared. So whatever the circle area was, we just divide it by 4, we times it by a quarter. In this case, the radius is 6. We can just see that on the diagram. So this is a quarter times pi times 6 squared. I'm doing this as if it was a non-calculator question because you could quite often get something like this on non-calculator. Quarter of 36 is 9, so it'll be 9 pi. And again, don't forget units, centimeters squared. Okay, how about this one? We've got 4 equal circles. We want to find the shaded area in terms of pi. Now that shaded area is going to be equal to the area of the square, take away the area of the circles. So we need to know two things. We need to know the area of the square, which is just 12 times 12, so that's just 144. And then what about the circles? Well, to find the area of a circle, we need its radius. What's the radius of that circle? Well, we know it's 12 all the way across, so halfway across, which is the diameter of one circle, should be 6, so your radius should be 3. So one of those circles is going to be equal to pi times 3 squared, which is 9 pi. Now again, we want to find this in terms of pi, so we should just leave it like that. But there isn't just one circle, there's 4 of them. So we'd want to do 4 lots of 9 pi. Let's simplify that down a little bit. 4 times 9 gives me 36. And that's actually it. You don't make that any simpler. You could work it out and it's like 30.2. But the question doesn't want it rounded at all. It wants it exactly. It wants it in terms of pi. So we just leave it like that. And again, remember units, centimeters squared. Okay, for the next one, we're going to have to reverse the formula. So we want to find the lengths of these sides. We start off with trying to find x on the right. Let's split this down the middle. I do point out these are different x's, which probably is not quite proper to do it this way. I should call one y, but there we go. So we've got an area of 10, and I think the best way of doing this is writing down the formula for area. We know it's pi r squared. We know it's equal to 10. Now what we're going to do is we're going to find the radius. So we're going to do that by dividing by pi. We could write that as 10 over pi. And because that's going to give us r squared, we're going to square root all that to get what the radius is. If we do that, we'll get that the radius is 1.784 centimeters, but we don't want the radius, we want x. And x is very clearly the diameter of that circle, so we will double that to get x is 3.57 rounded to do decimal places. 3.6 will be fine as well. For the one on the right, there's a very common mistake here, which is people do not see this pi symbol here. They just treat this as if it said 36. So it actually says 36 pi, but we're going to treat it the same otherwise. So pi r squared, the area of the circle, is 36 pi. And we're going to divide both sides by pi, and that essentially cancels them out. So we end up with r squared is 36. Then we'd square root it, and we get that the radius of that circle is 6, and x is the radius, so x is 6 centimeters. Cool. Let's keep going. So the next couple of questions are all about the circumference, and the circumference we're using either 2 pi r or more usually, really, I think you want to use pi d. So let's look at this first question. Now this is actually a distance, speed, time question. You can tell because it talks about speed, it talks about time. So obviously we're going to have to work out something to do with distance. Just as a reminder, your triangle should look something like that. Distance on top, speed and time on the base. So we want to find the distance all the way around the outside of this track, and that's kind of split up into 2 separate chunks. We've got these 2 straight lines. They're each 100 meters long, and so their total is 200. But we've also got these curved bits, and there's kind of 2 ways you can approach this. You could think about them as 2 semicircles, or you could think about them as 1 circle completely. I will do it as 2 semicircles to avoid some issues, but if you just treat it like 1 circle, this would still work. So what's the diameter of this semicircle? Well, 40 is clearly a radius there, so the diameter is 80. So if I want to find the circumference of this semicircle, I'm going to do myself 80 pi divided by 2. That will just be that bit there. But we've got 2 of them, so we want to add another 80 pi divided by 2. And if we stick that all together, we'll actually end up with just 80 pi. You could have just done 80 times pi because it's one circle overall. So our total distance, therefore, is equal to 200 plus 80 pi, which is 451.33 meters for once, not centimeters. Have we answered the question? No, because we want to find out about her time. Says she does the track at 18 meters per second. She wants to do this in less than 30 seconds. Does she succeed? Well, we want to find the time she took, so that's distance divided by speed. T equals D divided by S. So that will give us 451.33 divided by her speed, which was 18. And we'll get that it takes her 25.1 seconds. Did she succeed? Yes. Success. Because obviously 25 is less than 30. Okay, let's keep going. A couple more circumference questions. So on this question, there are two things that can catch you out. The first thing is units. This question mentions centimeters and kilometers. And really, if we want to do any sort of comparison, we're going to need to convert them both. So meters seems like a good halfway house between the two. You could change them both to centimeters, in which case you'd have 160,000 centimeters, I think. Or you could change them to kilometers, but this feels nicer. The second problem people have with this is that they'll just say, well, okay, we want to see how many times the wheel fits into the distance. So we'll just do 1600 divided by 0.6. But if you think about a circle, it's the circumference that's moving on the ground, not the diameter. So what we need to do is work out the circumference of this wheel. Well, we've got the diameter, so it's just pi times d. Which is going to give us 1.8849 ... It goes on forever, obviously. So full rotations, we're going to need to do 1600 for the distance travelled, divided by 1.88 for what one rotation is. And that'll tell us that it makes 848.8 rotations. Now the question does mention how many full rotations, so you could argue that this would be 848 full rotations and a bit left over, or 849 for you'd have to go that far to travel a full distance. Either of those would be accepted as your final answer. Okay. The classic one, the perimeter of the semicircle. So it says it's got radius 20. What do you think people will do? They'll just treat that as the diameter. Don't forget, if we want the diameter, we need to double our radius and say we've got 40 there. Now if we want the perimeter of this circle, it's equal to that flat bit we've just talked about. So it's equal to the diameter plus half the circumference. So it's equal to the diameter plus this extra bit around the side. And people will always forget to add in that diameter. So what we're going to do is 40 plus, and then half the circumference, so half times pi times 40. Simple as that. So simplify that a little bit. We're going to have 40 plus half of 40 is 20, so 40 plus 20 pi. And our final answer there is 102.8 meters. One last question to go. So this one, we've got a motor race covering 200 kilometers, and we want to know how many laps of the track cover 200 kilometers. So what do we need to know? We need to know the distance around that track. Now what does the track consist of? The track consists of 3 of these semicircles, these little semicircles. Now how big are they? Well, if this is 0.9 all the way down, and 3 of these fit into the same space, then each of these individual bits must be 0.3, and that's going to be like the diameter for our mini circles. Let's work that out first. So each one of those circles, we want to know pi times d, so pi times 0.3 divided by 2. And there's obviously 3 of those, so when we put it together, we're going to need to do that times 3. Then we've also got the large semicircle, and that's going to be pi times 0.9 over 2, pi d over 2, because it's half of a big circumference. On top of that, we've got our two flat lines, and each of those are just 0.75. So if we want to find our perimeter, we're going to need to add up 3 lots of this pi times 0.3 over 2, whatever that ends up being, plus this pi times 0.9 over 2 for the big semicircle on the side, plus the two 0.75s. Stick that all in and we'll end up with 4.33 kilometers for our perimeter. Now how many laps do we need to do? Well, if each lap is 4.3 kilometers, we need to see how many times that fits into 200. So we'll go 200 divided by 4.33. Try and use the answer button on your calculator when you're doing this to keep it accurate. That would tell you that you need to do 46.2 laps. Cool. So that was a little, hopefully, recap, reminder of things to do with circles and how we can apply them to parts of circles. Next up, we're going to look at arcs and sectors. Cheers.